OK. What would happen if we used a hard cutoff? Maybe some of this story would be a bit more transparent if we'd done that, because we'd see that we were explicitly dividing up low energy and high energy physics. But there's a price to pay for that transparency. And here, effectively, everybody decides it's too high a price to pay, and so they use dim reg. So what type of prices would you pay? So if you did that, this loop here would actually have terms that are cut off to the fourth over lambda chi to the fourth. And that guy breaks chiral symmetry. There's no term. I mean, it's giving a constant term, and you're not seeing the derivative coupling. And that means effectively that there's no counter term to absorb this dependence in our L chi, because our L chi respected chiral symmetry. So that's kind of bad. If you had a cutoff, you'd also get terms that went like cutoff squared times the momentum squared, where 2 powers of the p are replaced by cutoff. And that, in this language that we used earlier, would break the power counting in the sense that we have a power counting that says that the loops should be suppressed by p to the fourth, and it's broken by this. And then you would need to absorb that and renormalize your leading order coupling. But effectively, all the renormalization would be doing is restoring your power counting. It's not doing something that you should interpret as really a physical thing. So it's just something to be avoided. And then finally, the physics that you actually want, which is the logs of the cutoff, would also be there. And you would do the same thing as you do in dim reg. You would absorb that in the higher dimension operators. OK, so we won't use a cutoff, because we don't want to think about things that are breaking power counting or messing up chiral symmetry. Another thing that's different about chiral theories versus gauge theories is the structure of infrared divergences. And that's because you have derivative couplings. So you have many fewer infrared singularities than you have in gauge theory. And in fact, you usually don't have any. And one way of describing that is that you usually have a good m pi squared goes to 0 or p squared goes to 0 limit of your results. So you can just explicitly take these limits and talk about the results in those limits. And if we look back at what we were talking about, it's like you get p to the fourth log p squared. So there's a p to the fourth multiplying the log p squared. So you're not seeing log p squared blow up because it's got so many powers of p multiplying it. Although our focus is on formalism, I have to at least give you one example of something predictive and phenomenological. So pi scattering is a nice example of phenomenology. And it's particularly nice if you look at it below inelastic thresholds. So you just have elastic scattering. So you could look at pi goes to 4 pi. And that's something you could actually look at in chiral perturbation theory. But if we look at just pi goes to pi, where we have not enough energy to produce 4 pions, then the scattering is particularly simple. It's just described by an S matrix, which we can enumerate channel by channel. And it's just a phase. Where this L is a partial wave phase, and the I is an isospin. So for each isospin and for each angular momentum state, we get different phases, but that's encoding all the scattering. So it's like doing non-relativistic scattering or very simple quantum mechanical scattering. And when you have an elastic scattering like that, there's something called the effective range expansion, which is a derivative expansion for the phase shift delta. And if you do it for an arbitrary partial wave, this is how it looks. So this is, again, something that you would find in a discussion of scattering theory in quantum mechanics. And you have a derivative expansion of this quantity p to the 2l plus 1 cotan of that phase shift. And the a's here and the r0 depend on what channel you're talking about. And if we actually just take the fact that we can, so this is a description from quantum mechanics. It's just true, irrespective of what theory you're talking about. As long as you don't have other channels you can produce. If you talk about it from Chiral perturbation theory, though, we can just calculate pi pi goes to pi pi. And if you do that, which Weinberg did, then you just get results for these coefficients. So I'll just quote a couple of them to you. So you just get parameter-free results, parameter-free in the sense that they just involve m pi and this thing f. This thing f is actually measured by pi on decays, so it's not an unknown. And then from that, at lowest order in Chiral perturbation theory, you have no parameters once you've fixed m pi and f pi. And you can just make predictions for these scattering lengths, and those are the predictions. And they're parameter-free. In the sense that I just said. Okay, so that gives you some of the idea of what Chiral perturbation theory can do for you.